And lastly, we're going to talk a little bit about magnitude. So how do we measure how big an earthquake is? So there's no doubt that you've heard numbers that come about when an earthquake occurs. That was a 6.0. That was a 7.2. That was an 8.3. And so although you might assume that it's the Richter scale, it is really not what we use anymore, although the idea is still sound. It's kind of a modified Richter scale. And so we'll introduce the Richter scale because it still holds true for a majority of earthquakes, but this new modified, this kind of moment magnitude, it's very similar. It still uses the base 10, so it's still kind of something we can relate to. But the idea was that Richter used earthquakes in California to determine this formula that he could use to figure out how much energy was released during different types of events. And he used that to measure a scale and then applied some values to that, some numbers to that. So it's really telling you how much energy. So a 7.2 is telling you an amount of energy released. And we can compare that to a 7.3 or an 8 and compare the energy released. More energy, typically more damage. And so one way he was able to calculate that was to look at the S wave amplitude. So as a very general rule, we could look at the height. So from our baseline here, we measure how high the highest S wave was recorded on my seismic station. And I can use that to figure out or rough out the amount of energy released. So I can compare that to another earthquake which might have had a really high amplitude, and then I can adjust that number to determine how much energy that one released. So what I really want you to remember from all this magnitude stuff is, one, the scale, the Richter and the moment magnitude that we're kind of using today is logarithmic. And so we can't just assume that if you have a 6 or a 7 that a 6 is just 1 times bigger than, or a 7 is just 1 times bigger than a 6. It's really 10 times bigger when we're measuring S wave amplitudes, the height of the S wave, which is related to ground shaking, right? So you can imagine that if I have an S wave that spikes up, and typically we measure those in millimeters, but 10 millimeters, and then that was for, let's say, in this example, an earthquake with a magnitude of 5. If I have a magnitude 6 earthquake, it would be 10 times that. So instead of 10 millimeters, it'd be 100 millimeter height. That's a big difference just going from one whole number on this scale. And so usually the thing that we want you to focus more on, and don't look at this equation that's just a general equation. You know that. But it is how it's a calculation they can use to get a magnitude. It's this right here, that the energy released between one whole number on the scale, the Richter and the moment magnitude scale that we're currently using, is 30 times. And so from any whole number, right, whether it's from a 5 to a 6 or a 7 to an 8, there's 30 times more energy released during those. And so as we move up the Richter scale or the moment magnitude scale, we can see that there's a huge change in energy. Imagine that you experienced a magnitude 5 earthquake, and then someone else experienced a magnitude 7 earthquake. So this is, right, 2 whole numbers up on the scale here. Now between a 5 and a 6, we said it's 30 times. Well, between a 6 and a 7 is another 30 times. So it's really 30 times 30. 900 times more energy was released during that magnitude 7 than that magnitude 5. That is a lot of extra energy. And so this is why the decimal matters, let's say. In a 7.2 or 7.5. It's like, what's the big deal? They're so close. Well, really, if we're saying that one whole number is 30, then roughly, a decimal is like 3 times more. So from a 7.2 to 7.5, there is a good 6 times more energy being released during that event than, the 7.2. And so that's a significant amount. And so sometimes there'll be some arguments, actually. Was it a 7.2 or 7.3? You think, well, who cares? Well, there is a lot of energy difference just between those small little tenths in this scale. So, but when we think about comparing, this is the kind of the number I want you to remember is the energy difference between one whole number, right? There's about 30 times more energy. It gives you an idea of why it's significant when we move up in the scale. And so on our scale here, we can see that this graph is just trying to show you that really large earthquakes with high magnitude numbers are very rare, right? So, sevens worldwide, there might be 20 a year. But these really tiny ones, 3, there might be 100,000 a year. Now, a 3 probably wouldn't feel that. But we can record them because we have instruments that can do that. So up in here, you're starting to feel them, but they're pretty minor in the damages. And once we get up into the 5s and 6s, depending on some other properties, rock type, and how the buildings were built, and people, and all this kind of thing, how prepared they were, all those things come into play, you can get more damage. But these are starting to get some bigger earthquakes. Luckily, they're not occurring very frequently. And these really big ones, maybe once every 4 or 5 years, once every 10 years for a big one like that. So and you probably kind of knew that, but just to give you an idea of how that compares, right? So the other scales we mentioned, so this is the moment magnitude scale that the USGS is currently, it's just a modified Richter scale, really. It's more accurate because they use more information about, what slipped and how much movement there was. And they're not just using the amplitude of the S wave. So they're using some other factors and some other calculations to determine the moment magnitude scale. So those more accurate ones might take a little extra. But they can get a lot of this information from reading the seismogram and things like that. And then one other scale that used to be used a lot and once again has been modified, is still used by the USGS, is called the Mercalli scale. This is a scale where we use Roman numerals because we don't want to confuse it with the other scales where we use actual numerical values. And so on a USGS site, after an earthquake, you might see a map like this where the Roman numerals are telling you where the most intense ground shaking was and damage occurred and where the least. And so we can kind of plot these little diagrams that show where the most damage was and where the least. And although in most cases the heaviest damage is near the epicenter, we do get some weird shaped things. Instead of just a perfect bullseye where you'd expect the damage to be equally kind of decreasing in all directions, this is where geology comes into play. What is the ground like? It behaves differently. What different rocks behave differently when energy is being moved through them? Different sediments behave differently. Different buildings are constructed differently. And so that can all attribute to damage and can also attribute to this kind of unusual shape that we might get instead of a lovely little bullseye. And so the modified scale is there. The original scale is just kind of here in the slides, but it gives you an idea of how it was first created. It was basically that there are these descriptions, and this is even a shortened version of the descriptions. But basically what would happen is after an earthquake, people would be asked their opinion about what happened, what they saw. And of course, originally they tried to interview or question people they felt were more apt to be better at explaining what happened, scientists or doctors or things like that. But they could ask but now you can record anything. If you experience the earthquake, you can actually report to the USGS what you felt, and they'll try to incorporate that into their Mercalli map. But you can see here that, once someone explained to me what they experienced, then I would kind of assign a Roman numeral to it, and then I could, interview a large area and kind of get an idea of where the heaviest damage was. But basically, once you told me what happened, I would kind of read this and say, okay, well, they felt it, but there wasn't much going on, not much damage. Maybe that was a 3 on the Mercalli scale. Or if I went somewhere else and, most buildings were destroyed and bridges and dams and holy crap, I might give it a 10. And then I could create my little, what we're calling a shake map or a damage assessment map. So the Mercalli scale, even the modified version, is really focusing on kind of damage, where the moment magnitude scales and the current magnitude scales we're using, like a 7.2 or things like that, is really focusing on energy release, and kind of that's the difference. The other difference you just want to be aware of is because of the way the Mercalli scale is calculated, there is subjectivity in there. Because I'm interviewing or asking or evaluating things without numerical, data, I'm just getting their opinion. You can interpret things differently, so there is some subjectivity that could influence a number. So we have to keep that in mind when we're using the Mercalli scale. Some people might excitedly tell us it was the worst thing they've ever experienced because it was their first earthquake, and might tell us it was worse than it is. And someone who's been in multiple earthquakes might downplay it, that it wasn't that big a deal, and tell us that it was not that serious. And that could throw off our evaluation a little bit. But overall, it's still data, so it's still useful to create a generalized map of the damage that occurred during that earthquake. So those are the two things you want to be aware of for the scales. And that's kind of all we're going to do this week. Once again, next week we'll focus on the hazards that come from all these things, the damage they do, how we can modify or mitigate some of those things, and some prediction methods.